Okay, good day everyone. So for today's presentation, we will focus on practice problem 6.1 from refrigeration. So if you still remember, we when we discussed the topic on refrigeration, there were 5 practice problems under 6.1 that I've asked you to solve it on your own. So here I will provide you with the solution skeleton again. So in this practice problem 6.1, so there will be some solutions discussed for all the 5 problems. So through this presentation, so you will know how to draw a TS diagram based on the information given in the question. And then once you've identified all the important points on the TS diagram, then you will obtain values of enthalpy from tables. So this will be both from the saturated and superheated table charts. And then you will then solve for heat removed from refrigerated space and heat rejected to the warm space together with the COP value. And some of the questions may also include calculation for isentropic efficiency. So let's look at question number 1. So in question number 1, we have an ice making machine that operates on a ideal vapor compression cycle using refrigerant 134A. The refrigerant enters the compressor as saturated vapor at 140 kPa. So this point is important for you to start on the TS diagram, and it leaves the condenser as saturated liquid at 600 kPa. Water enters the ice machine at 13 degrees C and leaves as ice at -4. So this is as a result of the refrigeration. For an ice production rate of 7 kilogram per hour, so you have an ice production rate given to you, 7 kilogram per hour, determine the power input to the ice machine. Now please note they also give you this extra information that 393 kilojoule of heat needs to be removed from each 1 kilogram of water at 13 degrees C to turn it into ice at -4 degrees C. Now you've seen that water enters the ice machine at 13, which is what is mentioned here, and it leaves as ice at -4. So for each kilogram of water that you turn from 13 degrees C to -4, you will need to remove 393 kilojoule. So here in total, our production rate is 7 kilogram per hour. So we might need this information later on. So the answer is given here, right? So let's look at the solution. So here is your TS diagram. So based on the information given, so we can see here that the refrigerant enters the compressor as saturated vapor at 140 kPa. So this is the line on the TS diagram. So point number 1 is here before it enters the compressor and leaves the condenser as saturated liquid at 600 kPa. So from here it leaves the condenser as saturated liquid. So because it's at saturated liquid, so it's point number 3 here, which denotes to HF, right? So here you have saturated vapor. Saturated vapor is exactly at point number 1, right? So this is ideal vapor compression cycle. So the line will go from point 1 to point 2 straight here. So to identify what's the work done by the compressor, we need to find what is the enthalpy at point 1, enthalpy at point 2, right? So the amount of heat rejected will be calculated based on enthalpy values of point 2 and point 3, and then amount of heat removed from the refrigerated space will be based on enthalpies at point 4 and point 1, right? So what we need to do now is we need to find the enthalpies of H1, H2, H3, H4, and I hope you still remember the formulas for QL, Win, and also Q dot H. All right, so let's look at the skeleton of the solution. So this is a skeleton that I've provided. So what you need to do is you just need to fill in the blank to get your answers, and then make sure that the final answer that you've obtained here matches with the answer that you have here. Right, so I want you to do this question on your own, but this is just a rough guide for you so that you know what to do and where to find your values for enthalpies, and also the values for your QL, right, W in, and so on. Right, so in order to find H1, we look at point 1 again. So H1 is nothing but saturated vapor, right, at 140 kPa. So we will need to go to the appropriate tables. So here you have table A12, right? So we go to the value that is given to us, which is the pressure. So we'll go to the pressure table, and then this is the pressure given. So we need to go to 140. So at 140, you find the corresponding enthalpy. So this is the column for enthalpy. So here you have enthalpy for saturated liquid, saturated vapor. So since it's mentioned here that it's a saturated vapor, so we will take the value for saturated vapor. So 140 kPa again. So if you find, extrapolate, and then you go here, your saturated vapor is this value. All right, so this is your H1. Now correspondingly, because we need this S1 value to find H2, so we need to find what is our entropy, right? So Sg at 140, so again go to 140, same row here, we found saturated vapor value, so you find what is your Sg. So that will give you this value for Sg at 140 kPa. So jot it down there. Next we focus on point number 2. Now point number 2, if you see, it's outside of the dome line. So the moment if it's outside of the dome line, we can't use saturated refrigerant pressure table anymore. Alright, so we can't rely on table A12 because now it's no more saturated. Now it is in the superheated region. Alright, so to find the values of H2 at superheated region, we will then need to go to table A13. As you can see here, superheated refrigerant. Right, so now let's look at the pressure. Our pressure at point 2 based on the equation here is 600 kPa. Alright, 600 kPa translates to or corresponds to 0.6 MPa, megapascal. Right, so because the values of pressure in the superheated refrigerant 134A table is given in megapascal. So we need to convert this into megapascal. That will give us 0.6 megapascal. Now if you remember, we found our S1 here, right? So we know our value for H2 is in this column under 0.6 megapascal. So now how to find the value of H? So if you still remember, we found the value of entropy here. Now if you look at your TS diagram, for TS diagram, the entropy for point number 1 is similar to the entropy at point number 2. So these will have identical entropies, so which is denoted here. Now we find our entropy here, so you will need to find a match here. So obviously if you find the entropy here at 140 kPa, which will give you 0.94456, and you don't have 0.94456. So for this you need to interpolate, right? So 0.94456 is between these two values, right? It's between these two values. So you got to interpolate between these two values and find out what is your enthalpy, and that will give you the value for H2 here. So once you got your H2, then we will move on to H3. So H3, if you notice, we are back into the dome line here again. So it's at the edge of this part of the dome line. And if you are here, then it is automatically considered as saturated liquid. So this is saturated liquid. We will then come back to our saturated refrigerant table. All right. And this is at 600 kPa. We find the pressure at 600 kPa. So this is the pressure 600 kPa. And we find the column for enthalpy again. So earlier for H1 we found the enthalpy for saturated vapor. Now it is saturated liquid. So we go to this column where it shows saturated liquid. We go down, corresponds to 600 kPa. We find that this is our enthalpy. So just jot it down here. And then we know throttling from 0.3 to 0.4. We can approximate the enthalpy for 0.4 to be almost identical to the enthalpy at H3. So this value is similar to this. All right. So that is how you obtain all the enthalpy values for 0.1, 0.2, 0.3 and 0.4. So once you've got that, then you move to the cooling load of this refrigerator. We want to know what is the cooling load, meaning to say that how much heat is absorbed. So earlier in the question they've mentioned that you remove 393 kilojoule of heat when you cool down 1 kilogram of water from 13 degrees C to -4, right? So but our mass flow rate of ice given here is 7 kilogram per hour. Now bear in mind we need to change this into SI unit. So before you substitute this here, you need to change this to 7 kilogram per second. So how will you do that? So 1 hour. So we have 1 hour is how many seconds? So I think you should know that, right? So convert the hour here into seconds. So this will give you 7 kilogram per 3600 seconds. So that is the value for m dot ice here. And what is your delta H? The amount of heat. So this is for each kilogram. So for each kilogram, we have 393 kilojoule. So you can substitute this value for delta H ice. So 7 kilogram over 3600, which will give you kilogram per second. And then delta H is 393 kilojoule, and that will give you the cooling load calculation that you're looking for. So once you got that, to find the mass flow rate, you can then substitute it into this equation. Once you know QL, H1 and H4 is known, and you can find the mass flow rate of refrigerant easily. And the power input to the compressor will then be calculated using this formula. Once you know the mass flow rate of refrigerant, substitute it here. H2 and H1 is known from here, and you will be able to get what is the power input into the compressor, which should be almost equal to this value, right? So bear in mind when you do your calculation, minimum you must have at least 2 decimal points, nothing less than that. So with that, then your accuracy will be there, so that the final answer here almost matches with the answer that is given here. All right. So that is the end of question number 1 for this practice. Now we will move on to question number 2. All right. So now we are at question number 2. So question number 2 is on again ideal vapor compression refrigeration cycle. So you have an ideal vapor compression refrigeration cycle that uses R134A as its working fluid, maintains a condenser at 800 kilopascal and the evaporator at -12 degrees C. Now you are asked to determine the amount of power required and this system's COP to service a 150 kilowatt cooling load. All right. Now based on this information, you will need to draw out the TS diagram. So here I'm not going to draw the TS diagram for you. Based on the example given in question 1, you should be able to draw out your own TS diagram, right? So I'll give you the skeleton of the solution again. So here you need to find again as usual H1, H2, H3 and H4, right? So this is the skeleton. Now enthalpy and entropy at state 1 are determined from the given evaporator temperature. Now look at the evaporator temperature. So here we have evaporator at -12 degrees C, right? So this is again ideal vapor compression refrigeration cycle, right? So based on your TS diagram, you should be able to refer to your tables as shown here, right? So we will go because this is for H1. H1 is always at saturated region, right? But it's at the vapor. So we will go to the temperature table now, right? So this is pressure table. We will not refer to pressure table for H1 because what is given to you is the evaporator temperature. So you go to the evaporator temperature. So here we have -12. So this is -12 degrees C. So you find from the enthalpy column here, what is your Hg? So -12, this becomes your Hg, right? Similarly, you must also find your entropy. So -12, this becomes your Sg. So those two values are obtained from this table, right? Table A11. Now enthalpy at state 3 and 4 is determined from the given condenser pressure. So what is the condenser pressure? Condenser pressure is at 800 kilopascal. So then now this is pressure. So you go to the property table and charts that gives you the pressure. So based on this pressure, you go find what is the pressure. It has to correspond to this 800 kilopascal. Now this is again at point number 3. So you will know that it is enthalpy, but you are looking for saturated liquid. So at 800, if you draw it properly on your TS chart, you will know that you are referring to saturated liquid. So that will correspond to this value, right? And we know because of throttling effect, H3 is equals to H4. With that, now you know what is your H3 and H4, right? So we know H1. Corresponding to H1, we also found S1, H3 and H4 is known, right? Now we need to find what is our H2. Now H2 in an ideal vapor compression refrigeration cycle, once you've drawn your TS diagram, you will know that the H2 is in the superheated region, alright? So H2 is in the superheated region. So here we will then use this pressure, alright? We will use the condenser pressure, right, which is at 800 kPa, which corresponds to 0.8 megapascal. So you go to table A13, which gives you superheated refrigerant. You go to the column that shows you 0.8 megapascal, right? And remember we found S1. So you will need to use this value to find the value of S1, see where it fits here, and then you interpolate to get what is the value for your H. And that will give you the answer for H2. So once you've obtained your H1, H2, H3 and H4, then we can work out the solution that is required, because the question is asking you determine the amount of power required, right? The power required. So the power required here, right? So we will need to use this formula, right, on the condenser. But remember what is given to you, 150 kilowatt of cooling load. M dot is not given, but you can then convert this based on this formula. So when you change your M dot to QL, right, so you will have correspondingly this value coming in. So this formula then is changed to this formula. Now you have all the values. QL is given here, right? H1, H2 and H4 is obtained from here. You will be able to find what is the power required, all right? And COP again straightforward. Once you know QL, W is found from here, substitute it, and you should be able to find your COP and compare with the answer given in the question, right? So that is question number 2. Now let's go to question number 3 now. Question number 3, we have 300 kilojoule per minute. Now remember again, this is minute. You must change this to second liter, right? So you have a 300 kilojoule per minute refrigeration system that operates on an ideal vapor compression refrigeration cycle with R134A as the working fluid, right? The refrigerant enters the compressor as saturated vapor and is compressed to 800 kilopascal. You are asked to show the cycle on TS diagram with respect to saturation lines and determine these two parameters, COP and power input to the compressor. Now these are the answers given. Alright, so first thing first, we will need to draw out our TS diagram. Now TS diagram is again drawn based on this ideal vapor compression refrigeration cycle. Alright, so I'll show you the TS diagram. So this is the TS diagram. Now if you look at this TS diagram, this TS diagram corresponds to ideal vapor compression refrigeration cycle. So you have your point 1 here, point 2, point 3, point 4, and the corresponding pressure values. So here we have 140 kilopascal, right? Enters the compressor as saturated vapor at 140 kilopascal. So this is your 0.14 megapascal here, corresponds to this, and is compressed to 800 kilopascal. So you compress it in the compressor until it reaches 800 kilopascal or 0.8 megapascal, right? So this is where the compressor work comes in. This is how much heat you absorb from the evaporator. This is how much heat you reject from the condenser, right? So let's look at the skeleton again. Similarly, we will refer to these two tables. All you need to do is find H1, correspondingly find your S1. Based on this S1 value and the pressure that you have at point number 2, you will find H2. But remember, H2 is from superheater table. So you will need to use saturated table. So saturated table 140 kilopascal, right? Point 1 again is at this point, so you will find Hg. So let's look at 140 kilopascal. So this corresponds to this value for Hg, and you must also find what is your Sg here. So those are the two values that you want here. Now H2 again is at this point. Remember, it's no more in the saturated region. So this is at superheated region. So for superheated region, you will need to use the superheated table, table A13. So what is the pressure here? 0.8 megapascal. So you have a column for 0.5 megapascal. Then you go to the column that represents the 0.8 megapascal. So here 0.8 megapascal based on this value of entropy. You find where is the entropy fitting here. Then use your interpolation to find what is the value for H. Right? And then we come back to our point number 3. Point number 3 again 0.8 megapascal, but this is saturated liquid. So 800 kilopascal. We go to the column that shows you our enthalpy. We find our saturated liquid HF. That will give you the value of 95.47. And H4 is equals to H3, similar, right? So once you got these values, then you can substitute it into these formulas to get your COP and also your work input. So do give your best, do try it, see that you are able to get it, right? So it's pretty straightforward. If you have any difficulties, we shall discuss this further in our next lessons, right? So we will now move on to question number 4. Now question number 4 here is interesting because you are asked to repeat our question number 3 by assuming an isentropic efficiency of 80% for the compressor. So now this changes your TS diagram. So because your compression is no more based on isentropic line, right? So these are the answers. So we need to repeat the whole problem again based on this isentropic efficiency of 80% for the compressor. So first thing first, again, as I've mentioned again and again, we need to draw out our TS diagram. So since this involves isentropic efficiency for the compressor, your TS diagram will look like this, right? So this is the actual path, right? and this is the isentropic part of the compressor. Right, so it deviates by this much. Right, so the isentropic efficiency is given by 80%. Again, we will need to find 0.1, 0.2. Now you have one extra point here called 0.2s. This is what we need to find as well, because you need this point, all right, to calculate out your isentropic efficiency, which is already calculated here. But you will need that formula to calculate some other values, which we will see in the solution. 0.3 and 0.4 are similar to what we have discussed earlier. All right, so let's look at this skeleton of the solution again. So we want to find H1. H1, you know, it's a saturated vapor. So you find the enthalpy, Hg at 140 kPa. You find what is your S1. Right? So S1 will give you Sg, right? So which is equals to this. All right. Now to find H2S, this is what is so interesting here. If you look at the line H2S, line 0.2s and 0.1, it is on a vertical line. So meaning to say that entropy for 0.1 here is also the same entropy for 0.2s. Right? So we use that information, and we know pressure at 0.2 is 0.8 megapascal. So knowing that from the tables, right? So this is in the superheated region. So we have found our S1 here. So this S1 is similar to S2S. So based on these two values, we'll go to the 0.8 megapascal. Again, you will need to do some interpolation. You will find the value of H here. Now this H is H2S, not H2. All right, please remember this is H2S. To find H2, we will then go back to this formula for the isentropic efficiency. So now you are given isentropic efficiency of 80%. So this is your isentropic efficiency, or this one here. So this you can replace it as 0.28. H2S is given from here. H1 is obtained from here. And now what we want to do is we want to rearrange this whole formula so that we get what is our H2. Right, so that will give you the value for H2, and this should not be a problem for you because this is at the saturated liquid region here. We go back to this table, 800 kPa, you find what is your HF, which corresponds to this value, substitute it here, that is same as your H4. Right, so once you got that, use this formula, find your COP, use this formula to find your work in. Now, you need to compare the answers that you've obtained in question number 4 and question number 3. Look at the differences, and then if you can, try to comment. We will discuss this in our next lessons. All right? So that is question number 4. Now let's come to question number 5. So question number 5 here, you have R134A that enters the compressor of a refrigerator, right, as superheated vapor. Now you must pay attention to this. Refrigerant R134A enters the compressor of a refrigerator as superheated vapor. No more saturated vapor. So if it's a superheated vapor, then it's no more at the line of the dome. It is outside of the line of the dome. So that is why on your TS diagram, it will be drawn outside of the line. The previous examples you see on a TS diagram, we have drawn our point number 1 on this line. But here it is out. Why is it out? Because it enters the compressor as superheated vapor. Alright. So the pressure is given. It enters at 0.2 megapascal and -5 degrees C. Rate is given. Then it leaves at 1.2 megapascal and 70 degrees C. Alright. 1.2 megapascal, 70 degrees C. Right, so you compress it to this pressure, and as a result of that, your temperature increases from -5 degrees C to 70 degrees C, as shown on the TS diagram here. Then the refrigerant is cooled in the condenser to 44 degrees C, right? So in the condenser, you need to reject this heat. So this is rejected in the condenser, right? So this is how you reject the heat in the condenser. So from 70, the temperature drops to 44 degrees C, right? And as a result of that, your pressure is slightly subcooled because it's slightly lower. It's no more at the saturated region. It is slightly subcooled, right? So again, you see that this is not at the saturated region. So this is slightly subcooled, right? Then it is throttled to 0.21 megapascal, right? Disregarding any heat transfer and pressure drops in the connecting lines, show the cycle on a TS diagram with respect to saturation line. So I've already shown you the TS diagram, but you should be able to redraw this again, right? You should be able to redraw this again, right? So please bear in mind, okay, should be able to draw the entire TS diagram on your own. Now, based on this question, you are asked to determine the rate of heat removal from the refrigerated space, right? QL, power input to the compressor, W in, isentropic efficiency of the compressor, right? Isentropic efficiency based on these two deviation lines, and the COP. So as usual again, we will need to find our H1 S1, point number 1. Now remember, this is no more in the saturated region. This is in the superheated region. So we will need to then go to superheated table, not saturated table. The reason is point number 1 is not here. Point number 1 is outside the dome line. So that will give you, based on these two parameters, 0.2 megapascal. So we need to find where is 0.2 megapascal, which is here, right? And you are also given the temperature, -5 degrees C. So -5 degrees C, you will see that it is between 0 and -10. So between this 0 and -10, you got to interpolate and then find what is the value for your H. It lies between these 2 points. So you got to interpolate, find the value, and that becomes your H1. Similarly, you got to interpolate for your entropy as well, right? So give it a try, see what you get. Then once you've got that, we will still maintain the superheated table because point number 2 is still at superheated region. All right. So you find your H2. All right. So once you got your H2, because we have 1.2 megapascal, 70 degrees C. So this is your 1.2 megapascal, 70 degrees C, which will give you your H directly. And remember, this is isentropic. So the moment it's isentropic, you need to find H2S as well. So to find H2S, remember the pressure is similar, but you have to use the entropy at point number 1 because entropy 1 and entropy 2S is same. So use those two information. Again, you go back to 1.2 megapascal. You find where is your entropy, which corresponds to this S1. And then you interpolate between them to find your H2S, which is here. Right? Then we'll go to our point number 3. Now, point number 3 is subcooled, but we can assume it to be saturated. We can assume it to be saturated liquid, HF, all right? The error associated with it will be very, very minimum. So it's okay if you assume H3 to be equals to HF at 44. So you will need to go back to your saturated refrigerant R134A, go to the temperature at 44, and then you find what is your HF here. So that will give you your HF, right? Although it is subcooled, but in our assumption, right, we will assume it to be here. Right, so you can use the value for HF at 44 degrees C, and then that will correspond to the same value for your H4 as well. So once you get all these values, you can find QL, you can find W in based on this formula because m dot is given. If you remember, this is your m dot, all right? you can also find the isentropic efficiency, and finally you can find the COP. So make sure that all your answers here corresponds to the answers that you have obtained here. So again, I would like to say minimum when you do your calculation, you must maintain 2 decimal points. 3 is even better, right? So that the final answer will have an accuracy that is shown here, right? So that will be the end of our practice 6 with question number 5.